In this problem, we'll be looking at three things that we have to do to figure out what the concentration of the gases are at equilibrium. So I've written it out more like in a picture than the text that was given to me. It said that we had copper solid, I put it here in red, just a piece of solid, and it's different than something being in the solution or in the gas phase. Remember, there's going to be a term we use for concentration. It's just going to be 1. It makes it real simple when one of your reagents or products is a solid. It's considered to have an activity, you might say, that's not reflected by concentration. It's just, since it's the surface of the solid, they give it, and it's not going to be changing too much in terms of surface area or whatever, its effect on the reaction is just going to be considered as far as the law of mass action a 1. So that's going to be true for the two solids. The copper oxide here in black I've put into this picture. And this is a closed, sealed container. It has two gases that are going to be at equilibrium present. But in the question it said the starting point was we have 2.9 molarity or 2.9 concentration of O2. It did not say anything about the SO2, which is the product. So at the very beginning here of any problem, word problem, where they're asking about what's the equilibrium concentrations, the first thing you have to do is consider, well, which way is this reaction going to go? And that's a reaction quotient kind of thing, Q. So we have to kind of think about first, I'll maybe put it at the very, very bottom, very first thing you have to do is consider Q. What is going on in terms of the reaction? Is it going to go towards product, or is it directed towards reagent? And so what you do is you find Q, and you see how that compares to K. If Q is much lower than K, you go to the right. If Q is much higher, then you have too much product, and you're going to go to the left. Well, in this case, we know it's got to go to the right because it gives us donuts for SO2. It doesn't even say anything about it in the question, how much SO2 you have at the beginning. It just says you start with 2.9 molarity O2 gas. I should have put that in blue. So let's go ahead now into the second step. The second step with any of these problems is always to go to the ICE table, ICE. We're going to write down initially what we have. This is going to be in molarity, and then we're going to look at the change, and we're going to have that just represented by X. Minus X plus X, and then we'll have equilibrium. Now, I haven't written down the K value here. I'm going to use this space below when we have to put the law of mass action equation together. I'll bring K back into the story. That'll be our second step. Our third step will be finding X using that law of mass action. So just kind of remember, you have to first consider Q and then go to the ICE table knowing which way you're going to go in the reaction. And then third, you're going to take all the information from your ICE table, put it in an equation, the law of mass action equation, to find X. So let's get started. So we know with copper oxide, we do not have to worry about molarity. We can just say it's, as far as in the law of mass action, later on, it's only going to have a concentration you might consider as just 1. It never changes. And the reason for that is because the solid's always present, and it's got a surface area, and it has pretty much an unchanging, you might say, reactivity. That's not, you push that to the limits, of course, and it wouldn't work. But we're just going to leave that one blank because we're not considering its concentration. We're not going to do the same thing for copper either. It's a solid. So in your ICE table, you don't consider it. Now for the oxygen, we know we have 2.9 molarity. Again, this is molarity, not moles. So if they give you in a question moles and liters, you got to set that to molarity by dividing the moles by liters. And we had 0 amount of the SO2. So of course our change is going to be minus X. Be careful, always look at the coefficient, because if we have a coefficient there on the oxygen, then the change is going to be that coefficient times X. But we don't, so we can just say minus X. We don't have a coefficient here. If we did, we'd take plus 2X if there was a 2 there. We don't, so we just say plus X. And again, you got to get this minus and plus right by knowing the first part. This having just oxygen and no SO2, I'm going to have a minus from the left side and a plus to the product side. All right, once we've done that, this gets pretty straightforward. We can just say 2.9 minus x is going to be one term in the law of mass action equation, finding x, and this one's just going to be x. So let's go ahead and use this space now and below just to go ahead and start working with K. They give us a value of Kc. That means concentration. This is a gas. They could have done it with Kp, but they say Kc. Let's just propose. We'll go with 1.65. It doesn't really matter what the value is. You have to bring it into this next step. You got to take these values as your concentrations at equilibrium and put it into the law of mass action. So I'm going to go ahead and box that in just because that's so important. We're going to take now these two values. And you say, well, they're not values. Well, yes, they are. As soon as we find x, we'll be able to find those values. So SO2 is a product. We're going to say x on the top, and we don't need to square it. We don't need to square it or cube it because there's no coefficient there. And on the bottom will be 2.9 minus x. Now, in many cases, we'll have to determine whether this is a value that's above 10 to the fifth or below 10 to the fifth and make shortcuts. But here, since there's no squaring or cubing, we don't have to worry about a complex equation that we're going to get, and therefore have to worry about using approximations. And we can't because K is not 10 to the fifth or 10 to the minus fifth. It's a pretty in the middle kind of number. So we don't need it though. We're going to move on and just solve for x. You say, well, how are you going to do that? Well, you can take and multiply both sides by 2.9 minus x. So if I do that, I'm going to go ahead and get my handy dandy calculator out if I can find it. So I'm going to go 2.9 times 1.65. 2.9, because I'm bringing it over to the other side. So I'm going to take and have this multiplied by both these terms. 2.9 times 1.65 is equal to 4.785. And we would have, of course, minus 1.65x is equal to x. And because this is again because I took this and multiplied both sides by, and of course it cancels on this side, but I get 1.65 times minus x is minus 1.65x, and then this times the 1.65, I get 4.785. Now all I have to do is bring this term over. That's going to be now 2.65x, because we're going to add to both sides 1.65x. Doing that to this x will give me 2.65x, and that's equal to 4.785. So now all I have to do is divide by 2.65, this 4.785. That gives me x is equal to 1.8, and we're just going to, for sig figs purposes, since they only gave us 2 here, we'll just say 1.8. You say, well, are we done yet? Well, we're almost done. You've done the hard part. You've taken and worked through which way the reaction's going to go. You've set up your ice table, check. And you've then used the figures at equilibrium to plug into your law of mass action and found x. And sometimes that can be hard, and you have to use approximations, but sometimes it can be easy because all these coefficients were 1 and we didn't have to worry about the powers. And sometimes we have to, I guess, use that quadratic equation. But in this case we don't. We have 1.8. So we can say at the very beginning, my 2.902, I can say, hey, just take 1.8 away from 2.9. 2.9 minus 1.8. And I would be able to say at equilibrium, this would have been equal to 1.1. There would be 1.1 molarity of O2 in the solution, in this gas in this chamber. And of course, for over here, our SO2 would be equal to 1.8. So if the question at the very end is asking what are the actual equilibrium concentrations of the gases, you'd say, oh, it's 1.8 for SO2 and it's 1.1 for O2. Well, we've made a mess of this page, but oh, it's a great thing because it's chemistry. Peanut.